Hey, hello there. So today I'm going to talk about the meaning of live question 42, trapping rainwater. So what we have here is is a horizontal line represents the flat ground, and we have some land with a certain height and width in this on this ground. And what we want to do is to calculate if it's raining, strictly dripping down from top to the ground. And after the rain, how many water will be trapped in this kind of geometry? So that's the question. The each piece of the land in there, it has exactly a width of 1, and the height is given to us by this input array of integers. So as an example, we have at the x value 0, the height is 0. The 1's location, the height is 1. 2's location, the height is 0. So you get the idea. The amount of water being captured in there is going to be where can we accumulate water in this geometry. That's going to be higher land in between some two higher land. So this one unit of water is trapped between a land of height 1 and another land of height 2. There are 4 units of rain here being captured by the left hand side is a land of height 2, and right hand side is a land of height 3. So 4 units of rain here, and another unit of rain in the right hand side there. So that's pretty much the question. So one way we can do this is to maybe just looking at this picture from left to right. And we first find a land of height 1. That's the current maximum highest land we can find. So whenever we see some location afterwards, when the height is lower than that, we have a potential to accumulate the difference amount between the two height. We have a potential to accumulate those as the final water in there, but it's just a potential. When we find another higher land afterwards, then we can be sure the amount of potential waters in between can be realized. So just as an example, let's say that we are at the location 0. The max height we have seen so far is 0, and the potential amount of water we can trap is 0. The total amount of water we accumulated is 0 as well. So we are at this low ground there. Then we move towards right by 1. We find it's a high land of it's a land of height 1. There's not going to be any kind of water accumulating yet. There's no potential yet. But when we move to 2, we find that the height is 0. So it's smaller than the maximum current height. So we have the difference, that's 1 minus 0, to be the potential. After that, we move to location 3. That location has a height of 2, which is actually larger than the previous maximum height. So the amount of water that we think its potential now can be realized. So we move that onto the accumulator and reset this potential, because now we are looking at the maximum height of 2. And then we move to 4. We have a ground of height 1, so we put the difference onto the potential. Then one step further, we find a location of height 0, so we put the difference onto the potential. Another step, we find a height of 1, so the difference is 1. We are at location 6. 0, 1, 2, 3, 4, 5, 6. Then at 7, we find a new height, which is higher than the maximum height. That's 3 here. So the potential can be safely moved onto accumulator and reset the potential. The maximum height now is 3. After that, we will keep accumulating potential. 1, 2, 1, 2. So it's going to be 6 when we reach the end. But we were not going to be able to find anything that's higher than 3 afterwards. So the potential is just going to be sit there. So this after this from left to right, we're gonna realize 5 units of RAM in the end. There is 1 unit of RAM that's missing. So what we can account for that is do the scan from right to left again. So do the same thing. This time we're gonna be able to pick up that unit of RAM. And so this leads us to a 2-pass algorithm, one from left and one from right. And all we need here is a couple of variables. So it's a constant space 2-pass algorithm. There's just one little potential problem that we need to deal with, is that if we have the dip there, the water trapping dip here to be if that has the 2 highlands, the 2 boundaries to have the exactly same height, then we're gonna account it for twice, one from left to right, one from right to left. That we can potentially double counting that. So the way to avoid double counting is to in one of the paths we set if we have a new height from later on iterations that's strictly higher than the previous maximum, we do the update. We move the potential onto the accumulator. In the other direction, we will scan. We can have it to be strictly to be greater than or equal to. So the this kind of case will be only counted for once in the 2 pass. So that that's just the case, a little bit special case when we need to deal with in the code. So yeah, so let's code this solution. We're going to initialize a couple of variables: maximum height, potential, and accumulator. So they are all 0 in the beginning. And we're going to have 2 paths for height. This should be heights, right? If we have a height that's larger than or equal to, so this is the left to right pass, we use greater than or equal to. So in the latter right to left pass, we're gonna use strictly greater than. If it's greater than the current maximum, that means we can move the potential onto the accumulator. And we have to reset the potential to be 0, because we effectively looking at a new pond, new dip in there, new water trap, concave kind of shape in there. So that's why we reset this, and we have to update the maximum height because we are looking at a new pond with a new left-hand side boundary height value there. Otherwise, we would just try to update the accumulator by the difference between the maximum height and the current height. So that's the left to right scan. After that, we have to reset the maximum height and the potential to be 0 to reset those 2 values, and do a right to left scan. So basically just copy and pasting, and doing this in a reversed order, and change this greater than equal to strictly greater than, so that we don't double count this kind of case. And in the end, we just return the amount of water we accumulated through the 2 pass. So it looks right to me, so let's just go ahead and submit. We got an error. Okay, so what's the problem? Oh, I'm so sorry. This potential should be updating, not overriding. So that's the 2-pass algorithm, and it's pretty intuitive and straightforward. The problem with this solution is that we we actually can, you know, we are trying to accumulate this kind of to update this potential, and we have to wait later on when in the iteration when we find a location that's actually higher than the current maximum. Once we see that, we can move the amount of water in the potential onto the kiln. So if we do two, that leads us to the two paths. If we just do one pass with 2 pointers, one from right and one from left and one from right, we can have one of those to be higher than the other side. If that's the case, we don't need to put anything on the potential, because we know on the other side we have something that's a land that's actually higher. So everything just gonna be directly put onto a kiln. And when we find the one side to be higher than the other side, if they change which side has a higher land, we just change the way the direction we move the pointers. So if the right hand side has a land that's higher than the current left hand side land, that's the in the variables pointing to, we just try to move the left towards right. Every location along the way, instead of putting that difference onto potential, we can directly putting that onto the accumulator. If we find the left hand side now is at a location piece of land that's higher than the right hand side maximum, then we change the direction we move the variables, so we decrement the right hand side. So as an example, we have left and right pointing at 0 and 1. Since that the 1 at the right is higher than the left, we move the left towards this location 1 here. Then they become the same. We can choose to keep moving the left towards right, since that we are pretty sure there's at least a height of 1 land towards right. This 1 unit of water would be directly put onto the accumulator. Then we find the left hand side become height of 2, which is higher than the 1 from here. So we move the right towards decrement the right to come to this land of height 2. So now they have become equal. So we go back to increment to the left location. All the water along the way will be directly put onto the accumulator, because we know on the right hand side we have a land of height 2, and so this 4 units of water will be directly put onto the accumulator. Then we find the left hand side, we find a land of height 3, which is higher than the right hand side, so we decrement to the right. This unit of rain will be directly put onto the accumulator again. Then when the left and right they meet in the middle, that's when we pretty much accounted for all the waters that can be trapped inside this graph. So it's really to get rid of this potential here. The reason why this potential here is in this two-pass algorithm is that when we're just looking from left to right, we don't know if the right hand side has something that's higher. So unless so we're waiting to the time that we find another higher ground, then we can move the potential onto the kiln. So in this 2-pointer 1-pass algorithm, we are pretty sure the other side that if the other side is going to have a higher land, that's why we are moving towards there. When we become the higher position, then we are moving the other. We're changed to move down the other direction. So that's So in that we don't need this potential here, and the algorithm just become 1 pass, and again still going to be constant space. So we'll have something like left and right, which indicates the left and right locations. They initially going to be the leftmost and rightmost. And we're going to keep track of the left maximum height and the right maximum height. they're going to be 0 in the beginning. So while we haven't successfully meet each other in the middle, if this is less than the right, so if right hand side has a higher ground, then we want to move the left towards there, and all the waters that can potentially be trapped there can be directly put onto the accumulator. So we compare the current one with the left maximum height. So if it's greater than or equal to the left maximum, we basically just updating the left maximum. And after that, we if it's the other case, meaning that we can put some units of water onto the accumulator. So the water gonna be moved onto there is gonna be the difference between this and the left maximum. So after that, we're just gonna increment the left. Otherwise, it will be the other way around. So we just do a copy and paste and change the left to the right. In this case, right, and right. So here we decrement the right. In the end, we return the amount of water that's being accumulated. So this gives us the a strict one-pass algorithm with 2 pointers, and yeah, I think it's pretty much it. Let me just finally double check. Okay, yeah, so that's the code. Let me submit. Okay, slightly faster. Anyway, based on the analysis, you know that it's pretty much optimal. It's just one pass and a few variables, so it's constant space. And yeah, that's the question for today. The meaning of life.